if whenever you think it's appropriate, you can zoom in, do it, just do whatever you want to do.
I'll see if I can figure this out.
Okay. So, yeah, get my good side.
Oh wait, you want me to record you?
So the weight of a 70-kilogram astronaut on weight is, this is one of the formulas that you've got and you'll have on the test. I'll give it to you. Mass times gravity. Gravity varies depending on where you are. It's 10 on the Earth, or approximately that, and then the other places is different. So weight on the Earth is set your mass times gravity, 700 newtons. Somebody got 700 when they were doing this, and I heard them say, "Oh, that can't be right. It's too much." But I think they were thinking it was going to be pounds. And a newton is about 1/4 of a pound, so it's not that much. On the International Space Station, I didn't really need to do the math, but I just wanted to show that if you do the math, you still get a sensible answer. That's 70 kilograms of mass times no gravitational acceleration gives you no weight. And then on the moon, 70 kilograms times a smaller acceleration of gravity than the Earth gives you 112 newtons. Number 2, A and B, the nice, well, I don't know if it's nice or not. The kind of nice thing about number 2 is that you'll get quite a bit of more practice with these things on the lab part of this test. I'm choosing to do a lab part where you're figuring out accelerations of cars. So if you practice that, that should help you on all of these calculations on the constructive response part of the test too. So I think you'll get good at these if you study. The acceleration of this car is just change in velocity divided by change in time. The car starts from 0, goes up to 20 meters per second, so that's its change in velocity. And it does that over 4 seconds. 20 divided by 4 is 5. If you didn't use the formula, you could just think to yourself, acceleration is how much velocity I'm adding every second. If I'm starting at 0 and I've got 4 seconds, how much do I add 4 times to get 20, and it'll be 5. 2b, how much force is needed to do it? Force is mass times acceleration. You've got the mass, you've got the acceleration, multiply them together, and you get 5,500 newtons. Number 3, there's a, I don't know if you read this and interpreted it to mean, how do I figure out exactly how many kilograms of mass something has? Or were you thinking, how do I find out if it has a lot of mass or a little? You can use the same method to get a kind of a ballpark figure or to get an actual number. The easiest thing is if you're floating out in space, next time you're floating in space, and you have an object and you want to know if it has a lot of mass, what should you do?
Push it.
Push it. You could shake it, you could push it, and if you push it and you think to yourself, oh boy, that was really easy, and it went zooming away, what do you know about its mass? It doesn't have much. And if you push it and it's really hard and it seems like instead of it moving away, you get pushed backward, then it has a lot of mass. So that's really an answer. If you want to know exactly how much mass it has, you could float around out in space and get out a spring scale, hook it onto the thing, and pull. And watch the spring scale so you know you're putting a force of 10 newtons on it. And then you can have somebody else video it so you could calculate the acceleration of the thing. If you know what the force is and what the acceleration is, then you're going to be able to calculate the mass. But that's what you're doing when you're giving it a push. If you give it a push, and you feel like, oh, I exerted a really hard force and it hardly went anywhere at all, it accelerated slowly, then you know it's a big number. And if you thought, I didn't have to push very hard, and it went really fast, then you know the mass is small. The next one about the bike and the bus. Newton's third law seems to be a really big deal on this. There are a lot of questions where there will be something colliding with something else, and the question is, which one feels more force or which one experiences more force? And the answer is always going to be neither. If you've got a bus and you've got a bike and they hit each other, then the bike hits the bus just as hard as the bus hits the bike. And it doesn't seem like it because the bus keeps on moving and the bike reverses direction. But that's not because the forces are different, it's because the force is the same, but it affects the bicycle more because the bike has less inertia. And the bus has more inertia.
So does that mean that the impact force on the bike is greater?
Yes. No. The impact force on the bike is the same. if you start to think about this in terms of impulse, an impact force, and an impact time, it gets a little bit more complicated. It doesn't mean that you can't think of it that way, but I've just noticed that anytime people start thinking about impulse, they've got to be really careful. So if we, maybe I want to make myself a note. When we get to number 7, I want to come back to that, because 7 is really taking the same situation, except it's a bus and a bug, and then the bus is colliding with the bug, and we're talking about impulse. So I don't want to jump to 7 first, because I want to do 6 first. But when I get to 7, let's come back to 4. For now, just know that these two things are pushing one another. Don't think of it as impulse. Think of it as an action and a reaction. The bus pushes the bicycle, or the truck pushes the bicycle, and the bicycle pushes the truck. And according to Newton's third law, every action and reaction are equal. Even when we had the Newton car, and it was really heavy, and it shot the ping pong ball that way, and the ping pong ball went super fast this way, and the Newton car went super slow this way, which one was pushed by a greater force? The ping pong ball that went super fast, or the car that went super slow? Which one was pushed by a greater force? One was the action, one was the reaction. So the answer is neither. Actions and reactions are the same force. Now, what happens, the speed isn't going to be the same. The action speed and the reaction speed, those aren't the same. But if I apply a 50 Newton force to a ping pong ball, and I apply a 50 Newton force to a Newton car, that force is going to make the ping pong ball go really fast, and the Newton car not go fast at all. That's weird, but that's how it is. If the things are the same mass, if you had a truck hitting a truck, there would be the same force on both of them, and they both slow down the same amount because they'd have the same mass. Bicycle hitting bicycle, same force hitting one bicycle as the other, they both slow down the same amount because they have the same mass. The only thing that is ever really different is what effect that force has on the thing. The forces will always be the same. The effect will be greater on the thing with less inertia, with less mass. Emily?
Is the acceleration the same?
No. So can you follow me over here with the camera? The force formulas, force equals mass times acceleration. And if you solve that for acceleration, it's force divided by mass equals acceleration. So if you have here's the bike. Why did I decide to draw a bicycle? That's a bad bike. Oh, I know what I did. I need the front wheel up there. So anyway, there's the bike, and here's the bus. So when they hit, let's just say that the bike applies a 10 Newton force to the bus. It's way too small. We make it 1,000. And the bus applies 1,000 Newton force to the bike. You can calculate what sort of an acceleration that's going to have on them. The acceleration of the bike, let's just make the mass 10 kilograms. There's no rider on it. And the mass of the bus is going to be 10,000. That's a super heavy bus, but kilograms. So if you want to see what the acceleration of both of these things is going to be, for the bike it would be 1,000 divided by 10. And for the bus, you would have 10,000, 1,000 newtons of force divided by 10,000 kilograms. So that would be 0.1 would be how much the bus would accelerate based on that force. And how much the bike would accelerate would be 100. So 100 meters per second squared is how fast that bike's going to accelerate. And 0.1 meter per second squared is how fast the bus will accelerate. So that's just a way of quantifying what I was saying earlier. the more mass you have, the more the force is going to have an effect on you. Inertia is resistance to change in motion. The more mass you have, the more inertia you have. Inertia just means the same force is not going to speed you up, it's not going to slow you down, it's not going to affect you much. If you have less mass, you have less inertia, so the same force is going to speed you up or slow you down more. Is that I don't think there'll be any problems where you have to calculate that. Okay. Now the falling rock, I thought these were kind of weird questions. I don't really like these a whole lot because it seems like they're kind of pointless and not really testing you over what we've been learning, but it's okay. So a rock accelerates toward the earth. Does the earth exert a force on the rock? Yes. And why? That's the part that's kind of weird. I only really discussed that with you in a warm-up one time where I said, I think I might have picked two people and said they're attracted to one another. Because Newton's law of gravitation shows that any two things that have mass have a gravitational force between them, and you can calculate that. So, does the earth exert a force on a rock? Yes, because the earth has mass, the rock has mass, so they pull one another together. Any two things that have mass will do that. Does the rock exert a force on the earth? Yeah, for the same reason. And I think what they were getting at is, again, Newton's third law. If you have one thing pulling on another, then you're going to have the other pulling on the thing. You can't have an action without the reaction. So, does the earth accelerate toward the rock? Yes. It doesn't accelerate much. And you could go back to this formula again. You could calculate the acceleration. It would be whatever the force is that's exerted on the earth divided by the earth's mass. And this is huge. So when you divide something by a huge number, you get a really small acceleration. So yeah, the earth does accelerate toward it, but not fast enough to see it. And why? It's because there's a force applied to the earth. Anything that has a force applied to it is going to accelerate. But maybe not much if it's not real massive, if it's really massive. Any questions about those? Kind of just talked about those, the other one. Number 6, these, I've discovered that impulse problems are really tricky. So if, starting with number 6, you feel dumb, you're not alone, because a lot of people get confused with these impulse problems. And I'm not really sure why that is, but it is what it is. First off in this question, the question should have been worded differently. It should have said, 2 identical stuntmen fall from a building. It's kind of implied, but it's not said. It should have been. If they're not identical, you don't really know. One might be a big weightlifting stuntman, and the other one might be a skinny stuntman. So let's say they're identical. I've drawn pictures of them over here. So we've got Cool Bob, and you've got Flat Ace.
What if Flat Ace weighed less? Would that make
It would change. Yeah, it would change A, because you got the nice job. So when they fall, assuming they're falling the same distance, and see, assuming that if they are identical and they're falling through the air, they're going to fall at the same speed. So by the time they get to here, they're going to have the same velocity. That might not be the case if one of them's skinny and one of them's fat. They're going to have different terminal velocities. But even assuming they have the same velocity, when they get to the end of this fall, they have different masses. So by the time, if this guy was heavy, by the time he gets to here, he's going to have a big mass and low velocity, so he's going to have that much momentum. By the time this guy gets here, he's going to have a smaller mass, same velocity. So this would actually have more momentum than the other one. Your momentum depends on your velocity multiplied by your mass. So if it doesn't say that they're identical, then they don't necessarily have the same momentum unless you assume that they're identical in mass. So which one has the greatest change in momentum? Again, I guess it was not real specific. Are they talking about the change in momentum from when they start to fall until they hit? Or are they talking about the change in momentum from when they reach their maximum speed until they stop? It doesn't say, and it doesn't matter because it's the same. They both start out with no momentum. They both speed up to the same velocity. They both have the same mass, so they're gaining the same momentum. and then they both stop, so they're both losing all momentum. So no matter how you look at it, assuming that they have the same mass, they're going to have the same change in momentum. I feel like I'm talking so much that it's going to make it. Sometimes the more I talk, the more complicated it gets. But go back and watch this video if you're confused, and I think you can pick out the parts.
Oh, that's how
Where I won't. That's why we're doing this.
Okay,
I'll
really
post this, and if you want to go back and watch again, and you don't have to ask me to repeat things, you can just back it up. So, if you assume, if you buy into the fact that their change in momentum is the same, then their impulse has to be the same too, because that's what impulse is. Impulse is force times time. So when they hit, it's their impact force multiplied by the time of impact, but that is equal to change in momentum, just by definition. So if you run into a question like this, and you're asked for change in momentum, and then you're asked for impulse, your answer is going to be the same. Letter C, I've circled that one because I don't know why I circled that one. I think it was because I felt like they left one out. The question that I feel like they left out is, who has the greatest impact time when they hit? Is it going to be Bob who hits the air mattress, or Ace who hits the pavement? Who spends the longest amount of time hitting and slowing down and coming to a stop? Bob, because Bob hits the air mattress here, and he decelerates, decelerates, and decelerates, and then finally stops. Ace just hits the ground and wham, stops. So the reason that would have been a good question is it would have led you into the next question, which is, who feels the greatest impact force? If change in momentum really does equal impulse, then there are two different ways. They're achieving that change in momentum in two different ways. Flat Ace is hitting and suddenly stopping, so the stop time, the impact time, is really short. So to change momentum enough, he has to have a big impact force. Cool Bob is slowing down over a longer period of time, so to change in momentum, his force is smaller. To get the same stopping change in momentum, this guy has a small force over a long time, this guy has a big force over a short time. So C is Flat Ace has the biggest force. It takes a bigger force to stop suddenly than it does to stop slowly. And finally D really goes back to the beginning. Who has the greatest change in velocity? They're the same, assuming that they fall at the same rates, which they would if they're identical. All right, number 7. This is, and I mentioned that this is kind of related to number 4. It seemed like the questions you were asking, Jess, were more in line with this. So bus collides with a bug. Circle the best response. I'm going to show you a certain way to think about these, and if you start thinking about them in other ways, you're going to confuse yourself. It's okay. Sometimes it's a good experience. But I'm going to go in the way that makes the most sense. So first, I think the word feels is kind of screwy, because first, you could point out that the bus doesn't feel anything, and second, if I'm going really, really fast, and I'm a bus, and I'm hit by a 1 Newton force, it's not going to slow me down. I'm not going to even feel it. If I'm a bug, and I'm going really fast, and a 1 Newton force hits me, that's going to knock me backward. I would feel that. But I don't think that's what this question was asking. So I'm changing it to which experiences the greatest force. Bug hits a bus. At the same time, the bus hits the bug. Force is the same. So neither is the same. Which experiences the greatest impulse? So if you just keep in mind that this is what impulse is, it's that impact force, the force on the bug, the force on the bus, multiplied by the time of impact, you've got it. So if I punch myself in the face, does my hand spin longer hitting my face, or does my face spin longer hitting my hand? Or are they the same?
Same.
They gotta be the same. I can't hit myself for longer than I get hit. It just wouldn't make any sense. So the impact time of the bus and the impact time of the bug, they're the same, aren't they? And the forces were the same. So if the force is the same and the time's the same, the impulse has to be the same. So that's one where I think if you think about it in terms of change in momentum, you could get kind of confused. But if you just think it's the same force, it's the same impact time, then you got it. C, which one feels the greatest change in momentum? Well, if impulse is change in momentum, it's got to be the same answer again. Whatever the answer is going to be for the impulse question, it's going to be the same for the change in momentum question. Finally, we get to one that's different. The bug is going to slow down, or actually reverse direction. The bug's going to change velocity more than the bus. The bus isn't going to even notice it in terms of velocity. Jess, did that clarify kind of what you were asking about? Okay. Yeah. Good. Okay. This one, I'll just give you a second to check your answers, or a few seconds. And then I'm sure there'll be some shy people who won't say anything, and I'm just going to go over it whether you say I need to or not. I think people need to. The tricky thing about this, I really want you to notice that this is different from the way I did these things on all the tests and quizzes that I gave you. I had a scenario where there were a couple of things over here, usually cards with weights on them, and this was the before picture. And then over here, this was the after. Sometimes they'd be stuck together, sometimes they'd be moving apart. On the midterm, it's going to be more like this. You've got this row that's giving you information about what was happening before a collision, and then you've got another row that gives you information about after the collision. So you just fill in everything you can, and then you end up, in the end, you're going to end up solving for velocity. And to do that, you use momentum divided by mass. So in the top row, I could fill out, I think the entire top row. You got a 1,000 kilogram car, 2,000 kilogram truck. The speed of the car before the collision was 3, the speed of the truck was 0 because it was at rest. And then I could just multiply mass times velocity. Don't get confused here, they listed speed, but momentum is mass times velocity, mass times speed works. That's the momentum of the car, mass times speed gives you the momentum of the truck. Add them up to get the total momentum, and you're done with the before. Now, the important thing to know is that you can take that 3,000 and put it here. Why?
Momentum before is the same.
The momentum states the total momentum before some event takes place is going to equal the momentum after. That's the law of conservation of momentum. So move that down, and then I fill in everything else I can. It says after the collision, the truck has a velocity of 1. So the truck's mass is 2,000 times 1. I've got its momentum. Got the car's mass. These two things remain to be done. But if I know the total momentum, and I know the truck's momentum, then I know the car has to have that momentum. This is 3,000, and the truck provides 2,000 of that. The car's got to provide the other 1,000 kilograms meters per second. And finally, you can get the car's velocity by dividing its momentum of 1,000 by its mass of 1,000 equal 1. The last one, this was different in the sense that you have more information about the after situation than you do about the before, so you've got to go finish up the after stuff and go back, and in the very end, that's the answer that you get. If you got 9 meters per second for the car before, then you did this right. So everything's the same masses as before, and it says the bumpers lock and the two vehicles go 3 meters per second, so I put the speed as 3 for both of these in the after portion. And then I multiply mass times velocity to get momentum, mass times velocity is momentum, add the momentums, it's 9,000, which means the total momentum before had to be 9,000. The truck didn't have any momentum, so all that momentum had to be in the car. And finally, I can calculate the car's velocity, which is its momentum divided by its mass. Any questions about any of this stuff? All right, you can press the red button.